So, we will take a general topic called isomerism. These also come under the general organic chemistry. So, first let us define isomers. Isomers are the compounds having the same molecular formula, but different properties. Any two compounds with same molecular formula this is the first aspect, and however with different properties. Are called isomers. Now, here a small explanation. Molecular formula means it's not the structural formula, it is the number of atoms like carbon, hydrogen, like ethane represented with C2H6. Like that, the atoms in a specific order with the number of atoms we are mentioning. So, that formula is called molecular formula. So, any two compounds having the same molecular formula, if actually any two compounds means you have accepted these two are different compounds having the same molecular formula itself is the definition, but even then we say different properties. That means two compounds with molecular formula is same, but properties are different. Which properties? May be chemical or physical. And how many properties? It can be a one property or so many properties. That is also there is no restriction for the type of property, and the number of properties are not defined. Even one small property, a physical property different also, we take it grant they are isomers. An example, we have one compound called CH3CH2OH. This is called systematically ethanol, or up to this is ethyl with OH, ethyl alcohol, common name. Another compound with CH3OCH3. This is called methoxymethane systematically, methoxymethane. Now, these two compounds have the same molecular formula, that is C2H6O. This is called molecular formula. The number of carbons are 2 and 2, same. Hydrogen 6 and 6, one oxygen, one oxygen. But their properties are different. For example, ethanol has boiling point around 80 degrees centigrade, whereas dimethyl ether will have around minus 25 degrees or so. Very low boiling point. At 0 degrees also it is gas. At room temperature it is gas, isn't it? So there is a lot of difference between these two, the compounds. Solubility also, this is highly soluble, whereas ethers are not soluble. So many properties, it is not the number of properties, but even one property difference also, it is giving the definition correctly, that they are having different properties, but they are binded by the one particular aspect, that is the molecular formula. Such compounds are called isomers. Now, between these two there is some relation. What is that relation? The relation is defined as isomerism. Isomerism. Isomerism is the property or the phenomenon that exists. Between isomers. Any two isomers are between isomers. So, what is the phenomenon? Or the phenomenon you can replace with the linking property. What is the linking property? This is the linking property. Actually, the properties are different, that is not linked. So, what is linked means being the same molecular formula for two different compounds is nothing but that phenomenon is called isomerism. So, isomerism is the linking property or being the same molecular formula for the given two compounds is known as isomerism. Now, the isomerism is broadly classified into the two varieties, structural and the stereo. Structural is further divided and the stereo is further divided, that we will take up first. So, the isomerism classification, that is classification of the isomerism, it is divided into the, however, this is a very old pattern. We have different new the approaches are there, that we will take later, but let me finish off first in the old classical pattern. This is divided into the two types, that is structural isomerism and the stereo isomerism. These are the two types of the isomerism. In the structural isomerism, if a compound is built up with A, B, C, D, let us see. These A, B, C, D is rearranged in a particular pattern like A, D and B, C, let us say. The D is shifted to center. This type of the jumbling the atoms and getting another molecule which is having the same molecular formula come under the structural isomerism. In the stereo isomerism, it is not that. For example, if you have two methyl groups on a double bond on the same side and another compound, two methyl groups are opposite. Now, do you have that jumble the groups in order, means here that A, B, C, D order is reshuffled. Here the order is same, carbon, carbon, double bond, carbon, 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 double bond. Only thing is that methyl group, instead of going up, it has come down. So, what exactly difference is? The arrangement of groups in the space in a three-dimensional way, either up and down in a two-dimensional or in three-dimensional. The arrangement of groups in space, if the differs, the order is same, C, same order. Order being same, but the arrangement of groups with reference to the spatial arrangement, if it is different, such a type of isomerism is called stereo isomerism. Under the structural, we have 5 varieties. Structural isomerism may be classified into the chain isomerism further. Chain isomerism, position isomerism or positional isomerism, functional isomerism, metamerism, and tautomerism. All these 5 isomerisms are relatively somewhat easy to understand and represent the information also little easy when compared with the other type. Under the stereo also we have the 3 varieties: conformational isomerism, geometric isomerism, and optical isomerism. So, there are 3 types of the stereo isomerism, 5 types of structural isomerism, total 8 types of the isomerisms are there. One after the one we will take, and then with some examples let us make to understand this what type of isomerism. So, the first isomerism is a chain isomerism. This comes under the structural isomerism. That means the order, the sequence of the atoms are going to change, that is called sequential difference, or order of the atoms are going to change. The chain isomerism means this comes because of the difference in the chain. In fact, the chain means here carbon skeleton, just like we have a bones skeleton. In the organic compounds, the carbon-carbon framework is called skeleton of the organic compound. If that skeleton differs, then we call it the chain isomerism. The compounds with 1 carbon, 2 carbon, 3 carbons cannot make chain isomerism. That is a simple rule you can pass. Minimum 4 carbons. From this, the minimum number of carbons is 4 carbons requirement. With 4 carbons, we have one example. 4 carbons means there will be 8 hydrogens for a system of alkane. So, with this you can write the chain isomerism. These 4 carbons can be straight line, or 3 are in the straight form, 1 is in the branch form. So, the hydrogens, however, both will have the 10 hydrogens, that is not a problem, but the arrangement of the carbons, that is the basic skeleton is straight, basic skeleton is branched. Skeleton differs means it is the chain isomerism. Similarly, when 5 carbons are there, C5H, Cn, H2n plus 2, that means 12 hydrogens will be there. So, this straight 5 carbons will be straight. Always the straight chain is called N type, that is normal type. Whenever these 2 methyls with a long chain is called iso. So, these 2 are called N-butane and the isobutane. Similarly, we have a under the 5 carbon system also, there can be N type, there can be a iso type of the pentane, there can be a 2 branched, that means it is a neo type. So, all are pentanes, N-pentane, isopentane and neopentane. Now, the recognition also, if the compound with hydrogens, all other atoms, if they are confusing, you remove all the atoms and write only the skeleton of the compound. Compare the skeleton, if it is same, they are not skeleton, that is chain isomers. If the chain differs, then only they are called the chain isomers. So, with 5 carbon you have 3 chain isomers. A question may come, a pentane, how many chain isomers are possible for pentanes? So, formula may be given how many. This is only hit and trial method, you have to do it with a logically, first write straight one, then write 1 branched, then write 2 branched and so on, more the carbons, this is the way you have to develop it. However, some compounds we have common names, some have no common names. In this case, N, iso and neo are applicable. So, all these compounds, now these compounds, as I said, they have the difference in the properties. What properties means? All are alkanes, so they have the almost chemical properties same, but some physical properties, like for example, if you see in the van der Waals forces, that is intermolecular forces, I explained, longer the chain, surface area will be more. If the chains are in the branched pattern, it will be almost like a sphere, surface area will be less. So, another neo molecule, if it comes here, they come very close and leaving the gaps less. So, therefore, their more intermolecular attachments will be there, that means more van der Waals forces are involved. In the, as the surface increases more, the more number of the van der Waals forces. If the compound is a spherical shape, minimum surface area, so minimum the van der Waals forces will be there. So, therefore, naturally the boiling points are decreasing from N-pentane to isopentane, boiling points are decreasing. So, N-pentane more surface area, like that some properties are differing. Now, here what property and how many properties we are not concerned, but they having their difference in the skeleton. So, such isomers are recognized as chain isomers and they are verified, yes, there are some differences in the properties, therefore, we have to accept them as an isomer. If all the properties are same, then naturally they are nothing but the same compounds, we cannot say as a isomers. So, first of all, one point should be same, that means all these 3 compounds should have the same molecular formula. If the molecular formula is differing, one having 12 hydrogen, the other one is 10 hydrogen, they are not having they are not called isomers. The molecular formula should be same and the properties are different, means isomers. So, as the number of carbons, like for example, if 6 carbons are there, C6H14, it can be a straight chain, right? Always write straight one first, then 1 branched one, then 2 branched. These 2 branches can be both are on the second carbon or both can be alternatively like this. So, this is actually N-hexane or commonly hexane. This is isohexane or 2-methyl pentane, 2,2-dimethyl butane or neohexane. Common names are there, first 3 compounds. N-iso-neo. The other one has no common name, you have to go for the IUPAC name. IUPAC name for the neohexane is 2,2-dimethylbutane. This is 2,3-dimethylbutane. So totally how many compounds you got it? 4 compounds, right? So as the number of carbons increases, naturally we are going to get one more also, 1-methyl you can get. This is 2-methyl, this is 3-methyl. So both are 1-methyl groups containing. These two are 2-methyl. So totally 5 isomers are possible, 5 structural isomers are possible for the C6H14. Direct question may be asked. How many structural isomers are, how many chain isomers are possible for the C6H14? Answer is 5. Now let us take the second isomerism, that is positional isomerism. This isomerism is also come under the structural, that means atoms jumbling will be taking place, but with reference to the position of the some group, position of a group. What group means? It is not alkyl group, it is the functional group. So difference in the position of a functional group on a given chain. So we are having these certain words here. One is functional group. The functional group not having compounds, like alkanes have no functional group, so you can't get it. So in the alkanes, this positional isomerism will not come. Alkenes, there is a double bond is there, so you can have a double bond in between first and second, or second and third, like that. I say example 1-butene, 2-butene, double bond position is differing. So triple bond position, chlorine position, hydroxy position, like that. Position of a functional group is changing on a given chain. That means 2 given compounds should be same skeleton. If skeleton is different, we give preference for chain isomerism. So therefore chain will be same, but the functional group is changing. So minimum 3 carbons with one functional group, you can have this type of arrangement. 2 carbons with functional group you can't get like this. 2 carbons also you can get it, provided 2 functional groups. This 1,1-dichloro, 1,2-dichloro. Here only 2 carbons are there, but the 2 functional groups are there. So with one functional group, minimum 3 carbons are necessary. 3 carbons with one functional, can be on the last carbon, can be in the middle. So you can say 1-chloropropane, 2-chloropropane, or N-propyl, common naming, N-propyl chloride, isopropyl chloride. Isopropyl means germ dimethyl. You can write like this. Say this is isopropyl, then chloride. So nothing but the same thing, isn't it? Isopropyl means a bifurcated 2 methyls, just like a double-headed snake. So isopropyl group plus chlorine, isopropyl chloride, N-propyl. Now the skeleton is same for these 2 compounds. Even if you take this one also, skeleton is nothing. 3 carbons cannot make skeleton isomerism. So 3 carbon, whether you write straight or like L shape, makes no difference. And the chlorine on the last carbon, chlorine in the middle carbon. So functional group position is sliding on a given chain. The chain will be common. So therefore, for example, if 4 carbon compounds are there, chlorine can be on the first carbon, chlorine can be on the second carbon. This is called N-butyl. This is called secondary butyl. There can be another set. The 4 carbons can be branched also, like this. Now the chlorine can be on the terminal carbon or can be on the middle carbon. So these 2 are called isobutyl chloride and tertiary butyl chloride. All are the butyl chlorides, N-butyl chloride. So these 2 are called, first 2 set is called a positional isomerism, because the skeleton is same straight chain, 1-chlorobutane, 2-chlorobutane. IUPAC nomenclature gives much more clarity. Butane with 1-chloro, 2-chloro. What is different? Just position of the group. So therefore, if the position of the group is different, having the skeleton is same, then it is called positional isomerism. So, this is another set of positional isomers. Isobutyl chloride, tertiary butyl chloride is a set of that is a positional isomers, because skeleton is branched one. So, 1 chloro, 2 chloro. Okay. Now, if you take one compound from here, compare that one, whether the position is different or not, skeleton is different. Skeleton difference means they come under the chain isomerism. So, let us number like this: A, B, C, D. Right? A, B is a positional isomerism, C, D is a positional isomerism. A versus C or A versus D come under the skeleton isomerism, because straight chain, branched chain. If the skeleton differs, there is no argument for the positional. Given chain must be there, and in the both the compounds, skeleton should be same. Then only the position argument. I was in the first carbon, second carbon. So, like that, the group position you can discuss with reference to the same skeleton. So, therefore, skeleton you have to first compare. Skeleton difference is there, go for the chain isomerism. Skeleton is same, but the position of the functional group different, then positional isomerism. In the positional isomerism, what functional group you can change? You can change a chlorine like this, 1 chloro, 2 chloro, right? Yes. The chlorine is a clear functional group, so you can slide it on the main skeleton, you can get it. Similarly, you can skeleton a hydroxy group, yes, allowed. This is also allowed, positional and positional. You cannot do certain groups, like for example, a methyl is there and a methyl is there. If I say the methyl is on the first carbon, methyl on the second carbon, this is not allowed, because first reason, methyl is not a functional group. Second one, if you carefully understand, skeleton of the carbons is a straight chain. This is written as L shape, but it is a straight chain, it is a branched one. So, therefore, they come under the skeleton isomerism, not the positional. Similarly, the straight chain is there, but the COOH on the second carbon and the COOH on the third carbon. Now, if I say the functional group is COOH, COOH I am changing, right? So, you may take it as this compound as a positional isomerism, but really speaking, this carbon is also skeleton. It is not the total functional group. The carbon is also skeleton. So, therefore, skeleton of the compound means this is the skeleton here. So, what about the skeleton? Means skeleton is this one. So, skeleton is different. So, therefore, this is not called the positional isomerism, skeleton isomerism, that is chain isomerism. So, whenever the functional group has a carbon which is in continuation with the main chain, that carbon belongs to the skeleton only. So, therefore, a COOH group, an aldehyde group, a cyanide group, this type of the groups having the carbon in continuation to the main skeleton will go to the chain isomerism only. But whereas the groups, like for example, if a carbon is having OCH3 on the second carbon, OCH3 on the first carbon. Now, there is a carbon in the functional group, but this is allowed because this carbon is separated by the main skeleton through a oxygen, hetero element is there. So, a methoxy group is a clear group. This carbon will not go into the main skeleton, so therefore, it is allowed. 1-methoxy, 2-methoxybutanes are, that is chain, the positional isomerism. Therefore, position of the group, functional group is sliding on the main chain. Main chain is same, N-butane, N-butane. Methoxy group is. So, therefore, in some cases we are specifically marking like this. In the aromatic compounds like benzene, or in the cycloalkanes like cyclohexane, even methyl group's position is also, we are allowing these compounds as a positional isomers. What is changing means alkyl groups. Just now I said alkyl groups changing is not allowed. But in the aromatic and the cycloalkanes, even the functional group like COOH or the methyl groups type of the groups are allowed. They are called as a positional isomers only. 1 2 and the 1 3 positional isomers. If you take, they are positional isomers only. We are not allowing COOH in the open chain, but on the cyclic system they are allowed. And methyl groups are not allowed on the open chain, but here it is allowed. Both are positional isomers. Why you are allowing means, in the cyclic compound the ring itself is the skeleton. Outside whatever the group, whether it is homotype of the alkyl groups or the functional groups, whatever it is taken as an extra groups or functional groups, they are changing position, therefore positional isomerism. Now going to the third type of the isomerism, that is a functional isomerism. Functional isomerism. This is because of the difference in the functional group itself. Functional group will be different. That doesn't mean in one compound chlorine, the other compound bromine. These will not come under this category. For example, 1 chloro, 2 chloro and 2 bromo. What type of isomers means? Functional group difference are said, therefore chlorine, bromine different functional groups. That's not the case here. The molecular formula of these two compounds should be same. So therefore this particular set are not isomers. Functional group means again the molecular formula should be same, like as we have taken in the first example. One is alcohol, one is ether. The functional group is alcohol, this comes under one chapter, ether another chapter, but both are binded by the formula C6, H will be the 12 with O, and it C2 it is C2H6 only. C2H6O is the molecular formula for these two compounds. Both have the 6 hydrogens, 2 carbons and 1 oxygen, but one is alcohol functional group, the other functional group ether. Whenever oxygen is binded by 2 sides carbon means it is ether. So this type of functional group should be different. This is the simplest example for alcohols and ether make functional isomerism, right? Similarly, aldehydes and ketones. Aldehydes and ketones make functional isomerism. So like for example propanaldehyde and propanone. Both come under the same chapter actually, carbonyl compounds, but they are subgroups. Aldehydes is a subchapter and ketones is a subchapter of the same chapter, carbonyl compounds. Because of the presence of hydrogen directly attached to the carbonyl group, they have some fair oxidizable capability. Therefore, these having some difference properties when compared with the ketones. So the properties are different. So therefore, we are recognizing them as a isomers. So the propanaldehyde and the propanone, we have number of differentiating tests like tolerance test, failing, Schiff and so on. So therefore, the molecular formula is same, but their properties are different. Therefore, we recognize them as a not only the positional type, we can say positional, this is on the first carbon, second carbon, but the functional group itself is different. So therefore, this is an aldehyde and ketone, subgroups of the same chapter are allowed to classify as this type of the functional isomerism. Similarly, cyanides and isocyanides, NC and CN. Cyanides and isocyanide. This is isocyanide, second one is cyanide. And carboxylic acids and esters are COOR, provided both have the same molecular formula, like for example propanoic acid. Propanoic acid and methyl acetate both have the C3H6O2. This is the formula for both the compounds. So this being the same molecular formula, every time you have to examine. If the molecular formula is different, they are not at all isomers. So the molecular formula should be same, but the functional group is different. One belongs to carboxylic acid, the other one is acid derivative, specifically called acid ester. So they are different, so therefore their properties will be different, and physical chemical properties also will be different. But As I said, the number of properties and the quality of properties are not important. Even a very small property, if differs also, we recognize them as a isomer. So, carboxylic acids and the esters are the isomers. Many examples can be quoted like alkenes and cycloalkanes. Like for example, propene, CH3, CH double bond CH2, and cyclopropane. Both have the same formula C3H6, but one is alkene chapter that undergoes addition reaction, but the cycloalkanes, except few small members, other members are quite stable when compared with the alkenes. Like alkadienes and cycloalkenes and alkynes and bicycloalkanes. All will have the same formula, like for example, a butadiene, alkadiene, this is the most stable compound. Cycloalkene, that is a cyclobutene. Alkyne, either 1 butene or 2 butene you can take. Bicyclo compound, there are 2 rings are there, but number of carbons are 4 only. 4 carbons with the each one having 1 hydrogen. So, all have got the C4, H will be the 6 hydrogens, C4H6. Here 2 hydrogens are there, here 1 hydrogen. So, total 6 hydrogens, everywhere 6 hydrogens. So, they have same molecular formula, but all belongs to different chapters. So, definitely properties will be differing, and such a type of isomers are called what? A functional isomerism. So, some functional group belonging to, like for example, amines, 3-degree amines versus 2-degree amines versus 1-degree amines also. An example, trimethylamine and ethyl-methylamine and the N-propylamine. This is a 3-degree amine. So, all has got C3H9N formula. With this, these 3 types of compounds are coming. 3-degree means tertiary amine, secondary amine, primary amine. You can get one more primary amine, isopropyl amine also will come. So, a clear-cut understanding over the functional isomerism especially helps to, when you say frame a problem like I have 4 compounds, of which 1 compound so and so reaction gives, otherwise means if it gives a tertiary amine, immediately with 3 carbons what tertiary amine? Oh, trimethylamine. Like that, a grip over the isomerism. At later stage you can work out the problems even. So, the functional isomer specifically will give this type of the help in the working of the problems also. We will take the 4th part of this structural isomerism under the structural metamerism. To show the metamerism, the compound should have 2 alkyl groups attached to a functional group. The functional group should be made up of with either oxygen, nitrogen, sulfur and so on. Some hetero element should be there. Minimum 2 alkyl groups. You too can have a nitrogen with 3 alkyl groups, also applicable this case also. But minimum 2 alkyl groups whenever you have. A situation may be like this, an oxygen with 2 alkyl groups, right? I have 2 carbon this side, 2 carbon that side. It is a ether functional group, come under the class ROR. Now, what I do is 1 carbon decrease this side, shift to that side. So, still it is ether only, still it is ether only. So, the functional group is not changed, but the alkyl sizes are different. So, therefore, this type of isomerism we define the rearrangement of the number of carbons present in the alkyl groups attached to a functional group made up of with some hetero element to give another type of the arrangement. First I have 2 plus 2, now I have 1 plus 3. This type of rearranging the number of carbons without affecting the functional group nature, it is both are ether, that should be there. If this carbon also, if I shift that side, then it will become a butanol alcohol. Alcohols and ethers are functional. So, therefore, while shuffling this number of carbons, you must see that at least minimum 1 carbon should be restored. In the case of this is ethers case, you can have a 2-degree amines like 2 carbons are there. So, 1 carbon I decrease and 1 carbon I increase that side. So, this is a 2-degree amine. Second one is also 2-degree amine, both are amines. If this carbon also shifted, it will become 1-degree amine. As I said previous case functional isomerism, 1-degree amine, 2-degree amine, 3-degree amines are functional. Now, both are 2-degree, therefore, they are not functional, but the number of carbons are rearranged so that another isomer is formed. In the 3-degree amines also it is possible, like I have 3 alkyl groups attached to a nitrogen, which is a 3-degree amine. I can have a 1 carbon that side, you can make propyl and ethyl. 1 more carbon you can change butyl. Actually, this butyl can be 4 types. N type, this is right now N butyl, you can have isobutyl, tertiary butyl, secondary butyl. Similarly, a propyl can be 2 types, N type and isotype. 1 carbon, 2 carbon you cannot have any change, but whenever the more carbons are there, you can have option. So, the basically all are 3-degree amines. Okay. So, this is only 1 type, but here you have N propyl plus isopropyl also you can have, N iso secondary tertiary, but it should be a tertiary. So, both are tertiary. When you compare, then it will become a metamerism. You too can have a with sulfur also. You can have the groups like RCOOR, this is an ester. In the ester also there are some alkyl carbons are there. So, from this side to that side or that side to this side, you shuffle and see that the ester functional group is restored, but the number of carbons are jumbled. So, this comes under the metamerism. Jumbling of carbon from this side to that side will not come under the chain isomerism, because the 2 different chains are there. So, I am not changing the one particular chain. Both the chains are exchanged with the carbon. So, this is another type of the isomerism called metamerism. So, in the metamerism, it is we are rearranging the number of carbons present in the alkyl group attached to a functional group made up of with the hetero element. So, in some books we are seeing some, for example, if 2 carbons are there in a ketone, if I shuffle 1 carbon that side, it will become a ketone, but the other side propyl. This is not considered as a metamerism at all, because in the center there is no hetero element. This is all a pentane. This is 3 pentanone, 2 pentanone. According to the Morrison and Boyd, this type of example come under the positional isomerism, not the metamerism at all, because metamerism requires clear 2 alkyls or 3 alkyls or more alkyls attached to a functional group, which is separating these alkyl groups. Then only the reorganization of these carbons leads to give the same functional group, but the alkyl group sizes are different, therefore properties will be differing. And the properties also obviously very meager changes will be there in the properties. Functional group, actually whenever the alcohol and ether, 2 different functional groups, total the difference will be the functional groups. As I said, once again I repeat, it is not the how many properties, more the property is different, therefore good isomer, there is no such classification. Even a single small property, physical property, just like boiling point difference, yes, they are isomers. Stability, heats of the combustion, heat of hydrogenation, any one property differs also, they are called isomers. Fifth variety under the structural isomerism is tautomerism. Tautomerism is in fact there will be two isomers will be there in the tautomerism also, but they go on exchange mutually. Like for example, there is one compound called an alcohol with 2 carbons is known as 2 carbons, so systematically called eth. There is a double bond ene, the functional group ol. So systematic name of this compound is ethanol. However, this functional group up to here is called vinyl. So we have a common name called vinyl alcohol. Vinyl alcohol. In this vinyl alcohol, there is a chance of changing this compound into another compound, wherein the hydrogens this side are 3 now, that side only 1 hydrogen. So 1 hydrogen on the O is shifted to this carbon. They go on exchange in a equilibrium exists between the ethanol, and this is called systematically 2 carbons eth, single bond an, then aldehyde, so refer as Al. So this is ethanol, has a common name called acetaldehyde. Acetaldehyde and vinyl alcohol are said to be in equilibrium. This is one compound, that is another compound, but go on exchanges. So far we have not seen this type of the observation. That is neopentane is different and isopentane is different. They don't get exchange or interconvert. But here these two are isomers having difference in the properties and all that, but they get exchange. That means one compound if you prepare and put it in a bottle, the next second, a fraction of second, you find this compound changes into that one. Even if you prepare that one also, it changes into this one. How it changes means an aldehyde will have a phenomenon called hyperconjugation. In the hyperconjugation, its statement is whenever unsaturated carbon attached to saturated, the sigma electrons show conjugation with this unsaturated carbon. Consequently, the double bond polarized that side, a double bond is formed, O will become minus charge, hydrogen is cut and shown as a H plus, right? This is called a phenomenon between these two is called hyperconjugation. However, we have not studied so far. We will take this in the next the coming sessions. So this is called hyperconjugation. In the hyperconjugation, unlike this A compound B, these are two compounds are in equilibrium. Now B and C are not two compounds, they are nothing but same. In the resonance and its structures are nothing but same. They represent one compound, two different the structures. Whenever one compound exists in more than one structure, is called resonance. Like that, this is also a hyperconjugation is also a no bond resonance, or bond is open, and we are writing the resonance using the sigma electrons, sigma pi conjugation and so on. So this hyperconjugation, sometimes what happens, because of the minus charge proximity, the H plus may be allowed to attack on the minus, or the minus may attack here, vice versa. Then the H will have a bond there, and the compound changes into this type of the compound. Okay. So this type of the hyperconjugation structure of C changing into enol through this particular structure called hyperconjugation structure of B. This has no name. The compound C has no name. It is nothing but the contribution of B only. This compound ethanol is called compound B. Let us say What is C means? C is nothing but a hyperconjugation structure of compound B. It cannot be named as a different. These two are nothing but same. But whereas these two are different compounds having interconvertibility through a hyperconjugation structure. This is the mechanism, that is hydrogen cut, sigma electrons will come, this pi bonded electrons will go and become minus. The bond is cut. Once again, if the minus becomes here, the double bond goes back, you will get back that. These two are in fastly exchanging. This is not equilibrium, they are nothing but same. Equilibrium is different, two entities exchanging. There is only one entity which can be represented by two structures, is resonance or no bond resonance. So that concept is totally different. So like this, A and B, two functional isomers, no doubt, and they are exchangeable equilibrium. Equi stands what? Equi means equal. We think both are in the same ratio. But if you come to reality, aldehydes and ketones are more stable when compared with this type of enols. By virtue of the bonding sigma bonds and all that arrangement, it is proved that aldehydes and ketones are more stable. This particular enol only contributes to a 0.01%, I think. So this will be the 99.99% ethanol will be there. The percentage is only 0.01. Even then I am saying equilibrium. What does it mean? Means per a unit time, say 1 second or 1 minute or 1 hour, how many A convert into B, same number of B convert into A. So therefore the percentage remains same. This will be 99.99, that will be 0.01. Even after 2 hours or 10 hours, it will be same. However, equilibrium can be influenced by the external forces like pressure, temperature, acidity, basicity, and so on. Other factors may change. But after some time, again a new equilibrium will be set. The percentage may be different at that time, but equilibrium again set. So equilibrium will be going to be influenced by the external forces. A new equilibrium will be set. Again there will be a fast go on conversions. This is called enol and the aldehydes. When this enol percentage will have a chance of having more percentage, that is called what? Some examples, some more examples, let us see. This is a enol, right? Changes into what? The double bond comes here, hydrogen goes. So therefore this is a keto form of this one, this is enol form of this one. Both have different names. This is called 2-propanol, this is called propanone. Two are different compounds. And however, if you prepare one compound, the other compound comes immediately. Again ketones are more stable, enols are less stable. There is a changing through the hyperconjugation concept, and all that will be again discussed. And you have another propanol. This is also propanol. In this propanol, the compound changes into a carbonyl compound like this. Aldehyde comes. So this is in fact systematically called prop. En on the first carbon, second carbon. So therefore prop 1 en 2 ol it is. This is a prop 1 en 1 ol. There is another propanol. En is here, ol is here. Then this is called a prop. Numbering should be from ol side, right? So prop 2 en 1 ol. 2 en 1 ol. So this cannot have any tautomerization. Tautomerization is not possible. So therefore from enol side, which enol shows tautomerism means en and ol should be attached to a same common carbon. Then only it will have a keto form. Okay, enol can become into an aldehyde or a ketone depending upon this arrangement. En and ol should be attached to the second carbon. En and ol attached to the same first carbon. Here en is between the second and third carbon, ol is on the first carbon. This cannot convert into carbonyl compound. Similarly, eligibility can also be studied from the carbonyl compound. Which carbonyl compounds will become into enols means a carbonyl group should have either of the side one carbon having minimum one hydrogen. If this hydrogen is absent, you can't get. Example like A carbonyl compound, both the sides, no alkyl group at all. So, no tautomerism. No, this is called what? Functional group. Next is called alpha carbon. Alpha carbon hydrogen is called alpha hydrogen. No alpha carbon, no this. Similarly, if alpha carbon is there but replaced by some groups like alkyl groups, okay, this also has no chance of getting the tautomerization. Alkyl groups, when it is there, no alpha hydrogen, no tautomerization, no tautomerism. So, similarly, in a benzene with an aldehyde, alpha carbon is there but involved in the aromaticity. Like that, in several cases, we observe carbonyl compounds should have a alpha carbon hydrogen. That too, specifically, it is not the position, it is the phenomena hyperconjugation. Hyperconjugable hydrogen, if it is absent, it cannot give the tautomerism. So, therefore, from the enol side, E9 should be common carbon. From the carbonyl side, hyperconjugable hydrogen presence is the criteria for the changing the ketone into enol, enol into. This type of isomers which are going on changing is called tautomers. However, the percentage of the enols, that is called what? Several times asked in different examination, under what condition enol percentage will be increased or decreased. We have certain issues like. The first point is that is, we are going to see enol percentage or content. Enol content. Under what condition enol percentage will be 0 or more will be there? First point is presence of alpha hydrogen in aldehydes or ketones. A given aldehyde or a ketone, alpha hydrogen should be there, otherwise an enol percentage will become 0. Second condition, to get the more percentage, to get some percentage, this is the criteria. To get the more percentage, we need intramolecular hydrogen bonding. Intramolecular hydrogen bonding. This is one of the factor. Like for example, there is a carbonyl group. There is one more carbonyl group like this. Now this compound is known as what? Propane with 2 aldehydes. So propane diol. Or you can have a this side methyl, that side also methyl you can have. So it will become a 2,4-pentane dione. Okay. So in this case, what happens? Either this hydrogen can show, this hydrogen can show, this hydrogen also can show, this hydrogen can show this side. So totally all these hydrogens 3 plus 3, 6 plus 2, 8 hydrogen can show tautomerism. The middle hydrogen have got double chances. Total 10 chances are there to show the tautomerism. Now if accept this middle hydrogen shown in all form, then this jumps to the O. So you will get a enol like this, right? And this double bond is formed. This will be a methyl group. See here in this structure you are find some known structure. What is that? Benzene type of structure you can find, a 6-membered ring, right? A 6-membered ring has got some qualities. What is that? The deviation, bond angle deviation, you see every carbon is 120, there is no deviation, and 6 carbon rings are stable, verified in the cycloalkanes. And moreover here you have one more advantage. What is that? All these carbons are sp2 carbons, isn't it? 6-membered rings are more stable. Hydrogen bonding develops a new intermolecular force within the molecule. Within the molecule, one bond is added, so therefore stability increase. So all this together, so many hydrogens can make, especially middle hydrogen, if it shows all the carbons and the oxygen will have a required bond angle, stability. In addition to the next bond, one more bond is attached. So the stability comes, this exists almost 30% of enol. The enol content from 0.01 to 30% it is increased, right. So, if it is a 7-membered ring, let us say ketone is on the next carbon, the percentage decreases. So, the maximum percentage you find with the 6-membered, size of the ring, okay, and the number of the carbons involved in the, if this hydrogen comes here, this carbon will be saturated. Saturated carbons in the center is not that advisable. All unsaturated carbon planarity, and there is a conjugation in this system. If this double bond goes, this will become a double bond here, there is another double bond, there is no conjugation. Here we have one, conjugation is also their system. So, like that we have some plus points to this particular. So, intramolecular hydrogen bonding with the 6-membered ring, this is in addition. The rings with 6-membered is always advisable, and no strain on the bond angles. We do have another point that the acidic or basic nature also influence. Enols will have a acidic character, because enols, after losing the proton, if proton is removed, you will get enoxide. Enoxide have got a better resonance stability. So, therefore, the foregoing the proton is not a problem to the enol. If you remove the proton, enoxide is formed, it has a resonance stability. Therefore, enols will have this proton foregoing, that quality is called what? Acidic property. And if it becomes into the ketone, you do not have this type of the quality. So, the enols will have acidic property. When this equilibrium, if you add some base like sodium hydroxide, NaOH is added, the acidic compound turns up into the sodium salt. So, the more and more the proton liberated will react with OH, forms into water. So, most of the enol becomes into the sodium salt of enoxide. So, enoxide and enol together is the enol percentage. Therefore, in basic medium, ketones, all the ketones goes on change into the enols. So, enol percentage increases. In basic medium, more enol percentage. In acidic medium, what happens? The proton liberated, you are added acid. So, proton common ion effect shift the equilibrium that side. That means in acidic medium, more ketone percentage you find. Keto percentage increases in the acidic medium. Enol percentage increases in the basic medium. However, it has a limitation that more and more if you add increases, but after a certain time the total, if it is changed, still also increased, means it is not possible, isn't it? So, this acidic strength or basic strength is also one of the factor on this. So, the in basic medium enol percentage will be more, because enol and enol salt together we consider as a enol content. So, like this there are some factors which influence this enol percentage. Not only the aldehydes and ketones, the other compounds like for example nitroalkanes also can show this type of phenomena. Nitromethane can show this hyperconjugation followed by enol formation. The hydrogen is jumped, so therefore you may get a OH. This is nitroform of nitromethane. This is acid form. This is almost looks like a carboxylic acid, isn't it? And behaves also like just like carboxylic acid releases the H plus and undergoes resonance. This also the O minus can resonance. So, therefore, this will have acidic property. Therefore, it is called acid form, or people also say aciform of nitromethane. But both are called nitromethanes only. Nitroform and both are in equilibrium. Okay, like one alkynes can show tautomerism. There is one hydrogen. This double bond will come here. The 2 electrons will come here, and the pi bond shifts to here, and the detached hydrogen jumps on here. Similar the case the other side also, the 2 electrons are shifted and this is shifted, the cut hydrogen goes to here. So finally it will become into the triple bond comes in the center, and that will have the 3 hydrogens. So 1 butane changes into 2 butane through the double tautomerism. This is possible when it is added potassium hydroxide. When 1 butane is passed through the KOH, the 2 hydrogen shows tautomerism becomes into 2 butane. 2 butane happens to be more stable because of the 6 hyperconjugable. This has got only 2 this has 6 hyperconjugable, either side it can show. Whereas we have a method of preparing 2 butane to 1 butane also, pass into the sodamide. In the sodamide, once again 1 butane, they are equilibrium in fact. So 1 butane is formed, its sodium salt is formed. Sodium salt of the 1 butane will be formed. When you add water, you can generate the 1 butane gas. Right? 2 butane when passed through sodamide becomes sodium salt of the 1 butane. Same the reverse case of the hyperconjugation. Sodium salt, when you add water, proton comes and when between gas. Hyperconjugation is not possible in the solid compounds and the gases. Only either all the compounds in the form of suitable liquid solvent, or when the compounds are in the form of liquids itself, they show the so therefore when this gas passed through the solvent KOH becomes into 2 butane because of the stability. Why it is coming back means when it is passed through the sodamide solution, it becomes 1 butane gas. That gas, when you pass it through water, immediately again the solid actually passed through water, a gas is released. In the gas there is no back going, gas becomes stuck up and then it will become 1 butane gas is formed. 1 butane gas when passed through the KOH solution, 2 butane gas, that is in favor of the stability it is converting. So like this we have huge number of compounds which can show tautomerism. Tautomerism, a ketone for example, there is a ketone, this type of ketone. Already 2 double bonds are there in the structure, right? If this shows tautomerism, what happens? Tautomerism, you should not write this symbol. This is only used for the resonance and hyperconjugation. Resonance both are nothing but same. Tautomerism, 2 separate entities are there. So one of the hydrogen will show the tautomer, that is hyperconjugation, and then jumps onto that. So you will get a ene with OH. Already 2 double bonds are there. Now this will become aromatic. Because of the aromaticity, extraordinary stability to that 6-membered ring with a set number of electrons, planarity and conjugation gives aromatic nature according to the Huckel's rule. Now as I said, ketones will have more stability, but right now this ketone is having around only 0.001%. The 99.999% is for the aromatic phenol. This rare phenomena, enol existing in the huge percentage, can be expressed once again. That is aromatic stability. Aromatic compounds have got the extraordinary stability. So therefore, in some cases questions have come like this: which of the following cannot show that is tautomerism? Here we have unsaturated, it's a ketone no doubt, but if it is saturated I could have get. This is unsaturated carbon attached with unsaturated, all unsaturated only. So in the hyperconjugation I recall, unsaturated carbon attached to, we need a saturated. There is no such saturated carbon hydrogen, they are all unsaturated only. Therefore the compound cannot show tautomerism. This cannot show tautomerism. However, a compound like this can show. See, there is a unsaturated, again unsaturated, unsaturated, but this hydrogen can come here and can come here, can come here, like that. Then can this hydrogen can jump here, can form a tautomerism, which is again the phenol only. You will get back the again phenol. So immediately changes to the phenol. So this shows tautomerism because a unsaturated carbon has attached with saturated carbon with hydrogen. So eligibility criteria for the hyperconjugation is there. So this compound shows, but both the side ketones and like this means stuck up. There is no hyperconjugation for this system, consequently no enol formation for this compound.